Hi everyone, our final year project is about playing Chinese checkers with reinforcement learning. In this semester, we basically abandoned what we did last term and developed a whole new searching agent for generating the master move. In this searching agent, we have achieved a very high winning rate to the human player. We basically applies this following algorithm to speed up the searching. Basically, during the training, we applies 6 layers look ahead strategy, and we basically use the next scout searching. This searching is quite trivial and is it can well increase the threshold for the following mechanism. And for the transposition table, it is used to store the important moves and in the forms of hash value and return the value once the same board position is visited again. And for the heuristic table, it is used to sort the minimax tree such that the searching will reach its best speed. And for the board value assignment, here we can assign different board values and achieve different kind of strategy. And we basically developed the defensive, offensive, and the normal type of agent. And for with the help of this searching agent, we can combine it with the neural network. We basically have 3 neural network attempts. The first 2 are deep reinforcement learning, and the third one is the innovative and customized supervised network.
Alright, I'll give a brief introduction to our deep learning agent. First, based on the prior work in game agent developing, we can derive 2 sorts of deep reinforcement learning algorithm. One adopts off-policy strategy, while another is for on-policy. As the name suggests, off-policy agent will take optimal action each step, while on-policy agent takes the control policy into account during the whole training process. We have exploited one algorithm for each category: Deep Q learning from off-policy and Deep Salsa learning from on-policy, and observe that Deep Salsa retains a low tendency to run a risk step, while the converge time for Deep Q is much shorter. They have their own advantages against each other. Another breakthrough from our last term work is that we redefined the instant reward. Recall last term, we made use of 20 attributes, including the distance from the central line and advance gap, etc., to modify the reward. But we find in this way, the profit brought by some single delicate and detailed move will vanish. Hence, this term instead, we assign value for each hole on the board and use board value difference from the 2 sides to determine our reward. Moreover, a bunch of auxiliary techniques and algorithms are mounted to reduce computing complexity and to inject randomness into the network, like replay memory, which states in each iteration we pick up a state transition tuple into a replay memory, and then each time we sample the memory following some distributions, and fetch most frequently appeared one to train our network. The mechanism to best realize this process is called the priority sweeping. The network architecture contains 2 convolution layers with non-linearity, and 1 fully connected output layer, which resembles the work did by Google DeepMind Lab in 2013. Although the deep reinforcement learning against better result against our last term work, but it can defeat the heuristic research agent described previously yet. Hence, we intend to design a more powerful learning agent, and that's a starting point of our innovative supervised deep learning agent. The central idea is to leverage the result from the search engine to boost the agent performance and get improvement. The network is partitioned into 2 parts, and each part contains one sub-network. The first one is guided by each action taken by the search engine agent, while the second one uses the winning-losing status for the whole run as label. And the network comprises two fully connected layers, each with 729 nodes. Each layer is followed by a rectifier nonlinearity, and one softmax layer stands subsequent to the two layers to fix the output range. And our supervised network can beat the heuristic searching agent because we use the result of search engine, which looks up to 6 layers as input of our supervised network, and then we use the output of network as another bold value to train our search agent. And in other words, we can consider in this way, the search engine will finally look up 12 layers. And if we repeat this process and iterationally, we can achieve the global optimality by this supervised network. As a result, our customized supervised network gets best performance compared with the previous two. The guessing accuracy of the network, matching with the choice taken by the search engine, approaches to 0.75. The result is believed to be incredibly high given the randomness we introduce in the heuristic search agent. We can tell by the second chart that the learning agent gradually improves and defeats the search agent. Dramatically shrink of the performance may be due to the deadlock situation inside each gameplay, which can be avoided after the training runs accumulates. The following 4 graphs indicate the validation of the learning agent by playing against 4 different types of search agents with 6 layers or 8 layers, and defensive or offensive mode accordingly. Of course, the learning agent behaves better when fight against a layer offensive opponent. Thanks for listening.